Hi students, so welcome to another video on design of C amplifier. So in this particular design, let us design a C amplifier for a gain of maybe 30 volt per volt. So this is the magnitude. Let us assume the value of IC to be 1 milliampere, and let us assume the beta of the transistor as 100, and let us assume IS, the reverse saturation current, as 1 into 10 power minus 13 ampere. Let us assume the thermal voltage as 26 millivolts. So with these specifications and assumptions, so let us do the design of an amplifier with a gain of 30. So now what we are looking at is the design of this particular C amplifier. This is what we are looking at. So this is VCC, R1, R2, RC, V0. This is V in CC. So let us also assume that the supply voltage is 5 volt. As we know, some device equations are beta is equal to IC by IB, and collector current is given by IS into e power or exponential VBE by VT, from which we can write VBE is equal to VT into ln of IC by IS. So this is derived from this. And what else we have? We have the expression for the gain as AV magnitude is equal to GM into RC. GM into RC. And we also have GM is equal to IC by VT, which is now 1 milliampere divided by 26 millivolt, which happens to be 1 over 26 Siemens. Of course, we already know that okay, if you substitute this as 26 milli into ln of 1 e power minus 3 to 1 e power minus 13 happens to be 598 millivolt. So this is what is VBE. So since you know GM, using this particular equation, I can find the value of RC. So AV is equal to, magnitude is 30 is equal to GM into RC. So that you can write what is RC then. So then RC is equal to GM, okay, 30 by GM, 30 by GM, which happens to be 30 into 26, which is now, let me find out what is 30 into 26 is 780 ohms. 780 ohms. I think we have a 680 ohm standard resistance, or okay, this is 780 ohm. So maybe you can choose 780 ohm, or maybe we can use what is the nearest possible value. The 680 is there. After 680, I don't think any stand value. Okay, what you can keep is, you can keep RC as like 1 kilo ohm. This for this is choose. If RC is equal to 1 kilo ohm, then your gain, instead of 30, it will become how much? So it will actually become, so 1000 divided by 26, it comes out to be 38. So you'll be looking for a gain of 38. This is the gain that we'll be getting. Okay, fine. So now we will not look for a gain of 30, we look for a gain of 38, because we are choosing the value of RC closely to the available standard resistance, which is 1K. So we look for a when we actually measure the gain, it will be 38 volt per volt. Okay, this is fine. So RC is equal to now, so this is 1K. This is calculated to be 1K, so that it gives a gain of AV is equal to 38. So let us find out what is R1, R2. Maybe as we did in the previous case. So what is this? This is IB. This is I1. IB is now written as IC by beta, which is 1 milli by 100, which happens to be 10 microampere. Then I1 is equal to 10 times of IB, which happens to be 100. Okay, it is 100 microampere, which is equal to VCC R2 by R1 plus R2. Sorry, this R2 is not there. VCC by R1 plus R2 is also. So with VCC as 5, this as R1 plus R2. Then naturally R1 plus R2 will become 50k. So this is one relation you are getting using this expression where VBE is equal to 598 millivolt, which is also equal to VCC R2 by R1 plus R2, which is 598 milli is equal to 5 into R2 by 50k. Upon solving this, R2 becomes, I think, 5.98 kilo ohms. So that's what we found in the previous case. This is 5.98 kilo ohm. Then R1 plus R2 is equal to 50 kilo ohm. Therefore, R1 is equal to 50k minus 5.98 kilo ohm, which is supposed to be 44.12 kilo ohms also. So now you can use this as, okay, now you can redesign this. So let me tell you what we have to do is to get a gain of 38. So this is VCC, this is R1, this is R2, so and so. This is ground. So use this as 47 kilo ohm fixed resistance. Use this as a DRB and use this 1 kilo ohm. Since you are looking for a current of 1 milliampere, so how much it will drop? Drop is 1 volt. So how much is this? Is 5 volt. Since current is 1 milliampere, this is 1k, you're going to have 1 volt drop. So then this will be at 4 volt. So you adjust this R2. Now you can be careful now to get a gain of 38 volt per volt as your AV magnitude. You with this connection as it is, so use it as 0.1 microfarad. So Vin you can take it as 10 millivolt. For the time being, you just switch off this Vin. Don't apply any Vin. Keep this as 47k, keep it as 1k, apply 5 volts to the proper connection, vary this R2 so that this becomes 4 volt. If this is 4 volt, it ensures a current of 1 milliampere flowing through the cycle. If current is 1 milliampere, then GM is equal to 1 over 26. So if GM is this, so GM into RD, which is now 1 over 26 into 1000 will become 38. So this way you can able to get the desired gain of 30, which is rounded off to 38 because of a standard value of RC. Instead of 780, it is 1k. So the important thing is that when you are changing this R2, don't look for this as 2.5. If you are looking for this 2.5, you will not get a gain of 38. If you're looking for 2.5, then you are okay. Assume that okay, if you make this, if you adjust this R2 to make this as 2.5, then how much is IC? IC is equal to 5 minus 2.5 by 1k. So then this will be 2.5 milliampere. Then how much is GM? GM is equal to 2.5 milli by 26 millivolt. So then that will be how much? So now that will be 2.5 divided by 26 is it is 96.15 milli into 1000 you'll get a gain of 96. So if you make this equal to 2.5, then your gain will be then your AV will be 96 instead of 38. So that's what. So this 2.5 is to ensure that you have a maximum swing. So you have a maximum swing of whatever the available 0 to 5 volt. To have a maximum swing, you have to keep it at 2.5. To get a desired gain of 30, rounded off to 38, you have to make sure that the current flowing is as per your expectation. The current should be 1 milliampere. How to ensure that current is 1 milliampere? Make sure that this voltage is 5 volt. So for this to be 1 milliampere, what is VC? VC is equal to VCC minus IC RC. So this is 5 volt minus 1 milliampere into 1K. Can you see this becomes 4 volt? This is how it is becoming 4 volts. So make this 4 volts so that you'll get a gain of 38. So that you can able to design an amplifier for a desired gain of 30. I can say it's not exactly 30, it is made 38 because you are using 780 ohm resistor. Instead of 780 ohm, you are using 1K resistor. Hope you got this point. Okay, why it's not made as 2.5. If you make it as 2.5, it will be 96 is the expected gain. You can actually measure how much is the gain that you're getting. And let us do one design for a CC amplifier with the expected gain. This is CC amplifier. So I want to have a gain of AV of the, let this be 0.9. If 0.9 is the expected gain, how much should be the value of, what are the values of R1, R2 and RE? This is the circuit what you're looking at. This is VCC, this is CC, and this is coupling capacitor R1, R2, E0. This is RE. So let us see whether we have a standard value of RE for this 0.9, or shall we just see how much. So again, what are the assumptions? Let us assume IC is equal to 1 milliampere, beta is equal to 100. Of course, these are the things you should write while designing. Beta, and then IS is equal to 1 e power minus 13, or 10 to the power of minus 13, 1 into 10 power minus 13 ampere. Then what else? Vt is equal to 26 millivolt. Okay, these are the assumptions, and the equations what we have is beta is equal to, sorry, excuse me. This is one equation. Then we have IC is equal to IS exponential VBE by Vt, from which we can write VBE is equal to Vt ln of ISIC by IS. So what else you have? These are the things. And the equation what we have here is VB is equal to VCC into R2 by R1 plus R2, and VB is also equal to VBE, that is this voltage. This is VB, and VBE plus IE into RE, which is equal to VBE plus IC into RE. So what we are assuming is, so actually IE is equal to IC plus IB. Since IB is very small compared to IC, we write it as equal to almost IE is equal to IC. That's why it is so and so. So this is VB. voltage at base. And we have, let us assume a current of IB here. Let us assume a current of IB. Let us assume a current of I1. So this is what is IC. So then what you have in the okay, what is VE? VE is nothing but, of course, that's what is written, IE IC into RE. And we also have expression for, okay, this is already written. So with the specifications like okay, I have written the specifications. Then what is IB? It is IC by beta, which is 10 microampere. Then I1 is equal to 10 times IB happens to be 100 microampere, and I1 is also equal to VCC by R1 plus R2 is equal to 100 microampere, which is equal to 5 by R1 plus R2. This will give you R1 plus R2 as 50 kilo ohm. You know what is the summation of these two resistance. So later we'll find what is the value of R2. So how do you find the value of R2? Because R2 is related to VB. So what is VE? V is equal to IC into RE. So for finding RE, we have the expression of AV is equal to GMRE by 1 plus GMRE. This is what is the expression what we know for SCC amplifier. So from which GM is equal to 1 over, it's actually IC by VT, which is 1 milliampere by 26 millivolt. This will become 1 over 26 Siemens. So for AV of 0.9, for AV of 0.9 is equal to 1 over 26 RE by 1 plus 1 over 26 RE. So let us try to find out how much is RE expected. So let me find out how much is RE. So it is 0.9 alpha equals, open the parenthesis, 26 inverse into alpha A divided by 1 plus 26 inverse into alpha A. Close, shift cal. This is my, oh, what happened? 0.26. Oh, this is, it's actually 26 inverse into alpha E. Shift cal. Then RE comes out to be 234 ohms. This is the value of resistance. So then RE becomes 220 ohm. So let us choose a value of RE which is a standard value, which is 220 ohm. Now, since this is the value of RE for a gain of 0.9, so this is important. So this is the value of AV if RE is 220 ohm. So let us just again verify. 220 divided by 26. Okay, divide by 9.46. Yeah, I'll get 0.9. So this is so and so. So what we'll do is, so now this, what is VE? It is 1 milliampere multiplied by how much is RE? RE is 220 ohm. That's what I'm actually connecting. So this is 220 ohm. If it is this, is it not 220 millivolt? This is 220 millivolt. This is VE. How much is VB? This is actually VBE plus VE, which is 598 plus 220 milli, which happens to be 220 plus 598. This happens to be 818 millivolt is your VB. To get this much, you have this expression. No? Where is that? VB is equal to VCC R2 by R1 plus R2 is equal to 0.818. Keep in mind, this is the value of VB for a gain of 0.9. So maybe in the previous example, we have taken the condition that this should be a 2.5 volt. This should be a 2.4. This should be, with this has 2.5 volt, then this is some 2.2 kilo ohm or 2.5 kilo ohms. So now the consideration is totally different. The consideration now is you are looking for a gain of AV, which is 0.9, for which these are all the things. So now VB is equal to this much, which is equal to 5 into R2 by 50k. So look for how much is R2. How much is R2 now? So R2 now is equal to 0.818 alpha equals 5 into how much is R2? R2 is, okay, R2 need to be found, alpha A divided by 50k, 50 exponential 3. Okay. So now it is R2 should be 8.18 kilo ohm. So what we have to do now is, so if it is 8.18 kilo ohm, then how much is R1? R1 is equal to 50k minus 8.18k. So then this happens to be minus 50,000 will become 41.8 kilo ohm. So what you can do is you can use what is the standard value you have after 33. Maybe you can just use 33 kilo ohm itself, so it's not an issue. So now what you can use, so you can use R1 is equal to 33 kilo ohm. Use this R2 such that whenever you are using 220 ohm resistor, of course use a DRV, so that you ensure that the voltage here becomes 220 millivolt. The voltage here becomes 220 millivolt. Whenever the voltage here becomes 220 millivolt, uh, so then you are allowing a current of 1 milliampere, then a AP of 0.9 will be guaranteed. So you will have a DC voltage of 220 millivolts. So this will be 0. You will be having it at 220 millivolt. You have to apply a small amplitude so that you'll get the output voltage, which is 0.9 times the input. So this is VCC of 5 volt. So let this be 3.3k, of course 33k. Let us make this R2 will be slightly more than 8.1, so keep it around 9k, 10k. Of course certainly vary this so that the voltage here becomes 220 millivolts. So this should be 220 millivolt. So if it is 220 millivolt with this 220 ohm resistance, the current flowing will be 1 milliampere. The current that will be 1 milliampere will be flowing. If 1 milliampere flows, of course, we will ensure that AV becomes equal to 0.9. This is how you can able to dynamically change your design to any desired value. Even this can be 0.95. You can just look at the 0.96. You can also design for 0.8. You can just design for whatever gain that you want. Correspondingly, even the assumption of IC, which is 1 milliampere, it can be different. So I can just play with the things. So it's not necessary that the gain should be always equal to the current should be always equal to 1 milliampere. It can be even less or more also. So this can be different. So this can be different. So that's how you can do the design as per the requirement. Fundamentally, you need to know these equations. The equations that are required for CE amplifier is AV is equal to GM into RC should be known, and you should be knowing the expression for the collector current as IS into exponential VBE by VT, from which we can write VB is equal to VT into ln of IC by IS. And for the given circuit, so of course after writing the circuit diagram, write VBE is equal to VCC R2 by R1 plus R2. This is for CE amplifier. CE amplifier for a circuit which is something like this. What you have? Sorry, this is not there. This is R1. This is R2. This is what is VB. What you're talking about. This is V0. This is VD. R1 plus R2. And then you have expression for IC as of course IB is equal to IC by beta. You have the expression for GM as IC by VT. You have the expression for I1, which is the current flowing through the biasing resistor, as VCC by R1 plus R2. So all these equations you try to realize and then use it in your equation comfortably so that you can get the values of different biasing resistors. Okay, now just move on to the design of what else? maybe a square wave generator using uh, maybe 555 timer. So if you want to have a frequency of 500 hertz with a duty cycle of 20%, and maybe, okay, that's it. So now since it is 500 hertz, the total T becomes 2 milliseconds. Since it is 20% duty cycle, T on will become 0.4 millisecond, then T off will naturally become 1.6 millisecond. Since the duty cycle is less than 50%, you have to go for a circuit which is, so now I'm just doing the design part of it. This is VCC reset. You have the discharge, you have the threshold, you have the trigger, you have the output, you have the ground, you have the control voltage. This is this, so and so, R1, 2, this is grounded, threshold and trigger are shorted given to this is discharge, R1, R2, this is grounded, this is CS, this is C timing, R1, R2 is written, so we just provide a discharge path for this. So this is your charging, while discharging it goes through this, so this is only one diode is enough. This is VCC. Now we know the expression for T on as R1 CT ln of VCC minus VTL by VCC minus VTH. Again for T off, it is R2 CT ln of, it is VTH by VTL. It is VTH by VTL. Since this is a 555 timer, since VTH is equal to 2/3 of VCC and VTL is always half of VTH, it is equal to 1/3 of VCC. We will get okay, now you can actually find out what is T on, because I need to find what is R1, R2 values and of course the CT value. You can assume CT to be 0.1 microfarad. So you can use this as okay, now this is 0.4 millisecond is equal to R1. Let this be 0.1 micro. This is ln of 5 minus, okay, since it is 3.33, this is 1.66, it is 1.66, and it is 5 minus 3.33. Of course this happens to be 0.69, so which will be R1. Okay, let me just find the value of R1 here. R1 happens to be so it is 0.4 exponential minus 3 alpha equals alpha A into 0.1 exponential minus 6 into ln of upon the parenthesis double parenthesis 5 minus 1.66 divided by 5 minus 3.33. So R1 comes out to be 5.7 kilo ohm. 5.7 kilo ohm. If you solve for T off, so then it will be, so I'll just do the same thing, it will be again same. So only thing is that I'll make it, because it's the same expression, this is also 0.696 it comes out to be, so let me make it 1.6. 1.6 shift cal, I think it will be 4 times that. So now it is R2 is equal to 23 point, it's actually 4 times of this, 23 kilo ohms. So what you can do is you can use the nearest possible value, which is 6.8k. You can use 22k. Find T on T off correspondingly. So what will be T on? What will be T off? If you are using 6.8k, then it will be 6.8 exponential 3 into 0.1 exponential minus 6 into 0.69. So you will get of course on time of slightly increased on time, because this is more. How much you'll get is 469 microsecond. It is 0.469 millisecond. Instead of zero point 0.4, you'll get 0.469 millisecond, since I'm using a standard value of 6.8k, because there is no point in using DRBs to make your circuit complicated. If you use 22k, then this will be, I'll make this 22, that's it. Instead of that, it will be 0 to 2. So I'll make this equals, so it will be 1.51 millisecond. So then what is the frequency? Plus 0.469 exponential minus 3. So total time is 1.987 millisecond. 1 over that is 503 hertz. Duty cycle will be, it is 1 over this. Okay, over that into 0.469 exponential minus 3. It will be 23%. You'll get a 23% duty cycle. If you use, instead of 5.7k, if you use 6.8k, 22k, you'll get a design of this. So this is square wave generation using 555 timer. This is also a stable multivibrator. If you are asked to plot the waveforms, this is how the waveforms will look like. This is your output voltage, and the capacitor charging discharging will happen like this. This will go from VTH to VTL. So this is VTH, this is VTL. That's it. Of course, this can play with this, so it's not difficult. So they can ask for whatever frequency you are looking at. Of course, now suppose instead of having a control voltage of instead of having a capacitor there, if you put a battery here, suppose if I put some different voltage, I'll take out this, or I'll just forcefully make a voltage of 2 volt. If I make a voltage of 2 volts, then what is your T on? T on will become it is now R1. R1 is how much? It is 6.8k into 0.1 micro into ln of VCC is 5 minus, this is VTH, 5 minus 1 by 5 minus 2. Whatever 2 volt is there, that is actually VTH. So it's 5 minus VTL, because this is the equation, VCC minus VTL by VCC minus VTH. So then how much is this? So if you use a 2 volt, then you are okay. Well, let me write what is T off. T off remains the same. T off is equal to, again, how much is this? You have 22k as your R2, and the 0.1 micro into, this is 0.693, because it is actually, what is that? You have ln of 2 by 1. ln of 2 by 1. So ln of 2 is again 0.693. So your off time will be same as 1.51 millisecond. But your on time changes to, it is ln of 4 by 3. That into 6.8 exponential 3 into 0.1 exponential minus 6. That will become 195 microsecond. So whenever you use a capacitor, a voltage of 2 volt at control voltage, the T on will be 195 microsecond from 469 microsecond, and T off is same. T off is how much? 1.51 millisecond. So duty cycle will be now, it is 1. Excuse me, 0.59 exponential minus 3 plus 0.195 exponential minus 3, 1 over that into 0.195 exponential minus 3. So it will be 11.4% is the duty cycle. Then your T will be, or the frequency will be a bit more. So it is 0.195 plus 1.251. 1 over that is 586 hertz. This will be the frequency. From 503, this will become 586 kilohertz, and duty cycle will reduce from 23% to 11.3%. Off time remains the same. On time reduces from 469 microsecond to 195 microsecond. So this is how the things will change when you replace or when you have a control voltage which is other than 230 cc, Okay, this is how you can able to demonstrate or show that okay, control voltage will going to change the frequency of the oscillator, which is also called as a voltage controlled oscillator. This is an important application of 555 timer. So voltage will control the oscillating frequency. That's why it's called as voltage controlled oscillator. If you change this voltage, T on will change. Once your T on changes, naturally total T changes, which will change the frequency of the oscillations. Okay, now let us move on to the monostable multivator. So this is 555 timer based monostable multivibrator. So let us write the circuit diagram. So this is VCC reset. This is connected to VCC. I will have a resistor and a capacitor is grounded. This is connected between discharge and threshold. This is your trigger connected to an external trigger signal. This is grounded, and this is your control voltage. You connect the capacitor. This is CT, this is RT, this is output, this is 555 timer. So now assume that I want to have a pulse width of 6 millisecond. Pulse width of 6 millisecond. So now to get a pulse width of 6 millisecond, first of all I have to have a trigger signal whose time period is greater than T pulse width, whose T off of the trigger signal should be far less than 6 milliseconds. These are the requirements. And of course, the low amplitude should be less than VTL. The V low of your trigger signal should be less than VTL. With these specifications, we can actually get the. This is a must. So T of your trigger should be greater than pulse width. T off should be less than 6 millisecond. So let us assume that let T be some 20 millisecond. Let T off be something like 2 millisecond. Then what is duty cycle of this? So then duty cycle is equal to T on by T. Is it not 18 millisecond by 20 millisecond? And how much is 18 by 20? 18 by 20 is 90%. So let us have a 90% duty cycle with a frequency of 20 millisecond is 50 hertz. So you have to have a trigger signal whose low should be something like this. this should repeat, or from here to here it should be, this from here to here should be 20 millisecond, and this should be hardly 2 milliseconds. If this is your V trigger, this is with respect to time, then I'll get an output voltage. So as long as this is high, the output voltage will be low, output voltage will be low. Whenever your whenever the input trigger signal goes less than VTL, output goes to high state. It remains in high state for a period of, in this case, 6 millisecond. Yes, 6 may be somewhere here. It will come down here and then play again, go up whenever your trigger signal goes less than VTL. So this is 6 millisecond. Of course, if you see this capacitor, so this is V0. So capacitor will be charging up to VTH. It will be charging up to VTH. It will come down. This will charge up to VTH. This is VTH. So this is V trigger. So all of you know that T pulse width is given by RT CT ln of, it is VCC by VCC minus VTH. So now since VTH is 2/3 of VCC, so what will be this? It is RT CT ln of VCC by VCC minus 2/3 VCC. This happens to be ln of 3. Ln of 3 is 1.09 RTCT. So this is 6 millisecond. So let us assume CT to be 0.1 microfarad. Then how much will be your RT? Then RT is, so it is 6 exponential minus 3 alpha equals 1.09 into alpha A into 0.1 exponential minus 6, shift cal, it comes out to be 55 kilo ohms. RT comes out to be 55 kilo ohms. So you don't have a standard value of 55 kilo ohms. You can choose a RT of, how much? RT of 47 kilo ohm. Choose a CT of 0.1 microfarad, and of course this should be a must. So you should have a trigger signal something like this with a frequency of 50 Hertz, duty cycle of 90%, and with amplitude as 2.5 volt, offset as 2.5 volt, will guarantee a signal from 0 to 5, which will ensure that it is going below VTL. This will get a pulse width of, how much will be the pulse width? It will be slightly less than 6 millisecond because we are using a bit lesser value. Instead of 55 you are using 47. So it will be 47 into 1.09 into 0.1. You can see now it will be 5.123 millisecond. This will be the pulse width. Suppose if you change this to a voltage of maybe assume that you will apply 4 volt here. If you apply 4 volts using waveGen 2, so then what is T pulse width is equal to, it is RT CT ln of VCC by VCC minus VTH. VTH is now 4 because we have connected 4 volts here. So then this is 4. So then what will be this? With this as 47K, with this as 0.1 micro, ln of 5 by 5 minus 4. So then this is ln of 5. So ln of 5 will be, what is ln of 5? It is this much into 0.1 exponent minus 6 into 47 exponential 3. So you will get 7.56 millisecond as your pulse width. So instead of 5.13, we'll get 7.56 millisecond if you use a threshold voltage of 4 volts here. If you use a threshold voltage of 4 volts, meaning, so this will not be a 6 millisecond, sorry, this will not be a 5.13 millisecond, it will be a 7.56 millisecond, because you have changed the threshold voltage. So this threshold, which is VTH, will be changed from 3.33 to 4 volts. So that's it, the design of CE amplifier, CC amplifier, and a stable multivibrator and monostable multivibrator. Thank you.